Hello everybody and welcome back to another video. My name is Coordinatics, and in today's video we're going to be taking a look at this problem, barn tree, from the 2022 December contest USACO Silver. So without further ado, if you're ready to get started, let's jump right into it. Okay, so barn tree. So Farmer John's Farms has n barns numbered 1 to n. There are n roads and each road connects 2 barns, and it's possible to get from any barn to any other barn via some sequence of roads. So currently the Jth barn has HI hay bales, and to please his cows, Farmer John would like to move the hay such that each barn has an equal number of bales. So you can select any pair of barns connected by road and move and order his farm hands to move a positive integer number of bales less than or equal to the number of bales currently at the first barn from the first barn to the second barn. So just to note, the roads are bidirectional, so we can transfer from one road to another road. By the way, this is a live solve, so like I'm going through this live, like I have not read this problem before, and so that's why if I'm stuttering, it's because I have not read this problem before. So please determine the sequence of orders Farmer John can issue to complete the task in the minimum number of orders. So he wants to, so we got like some sort of a network, a graph. Are there n-1? There are n-1. So it's a tree. So we've got like a tree, so something like this, right? The classic demo tree, something that will look a bit like that. Okay. There we go. So we have a tree, and now each one is going to have some amount. Okay, so 1, 2, 2, 3, 2, 4. Yeah. 1, 2, 2, 3, 2, 4. Okay, so that's the sample test case is just this. Okay, so node 1, node 2, node 3, node 4, right? So node 1 has 2 bales, so let's do that in this color. Node 2 has 1 bale. Node 3 has 4 bales. Node 4 has 5 bales. Okay. So, and we want to indicate the order of the moves. Okay. So we got 4 nodes. Is there anything that they want us to do indicating that it's impossible? No. It's guaranteed. Okay. Looks like it's guaranteed that it's possible. Right, and so in this case, 2 plus 1 plus 4 plus 5 is 12, which means each one needs to have 3. Okay, so what does that mean? That means that anything with more than 3 needs to give its values away, if that makes sense. Right, so I'm going to erase these and indicate these by how much they need, and so then we can figure out what to do. So let's start off by, so here's what I'm thinking, right? We know that some node, for instance, this one, so this is going to be -1, right? It needs 1. This one's -2, needs 2. This one is positive, what was it? I think 1, and this one is +2, right? So we know that each one has to have 3, so that's why we've done this way. This is a positive. So what do I know here? Well, I know that this 3 right here is a leaf node, right? And this 4 is also a leaf node. So since these two are leaf nodes, they're going to just want to push any excess away. This one's also a leaf node, but it needs to steal stuff, so we can't exactly do that. Oh, we can. We can push a negative node, because that's the same as pulling a positive node. Okay, so what this means is, we can say that since this is +1, this is +2, and this is -1, I'm going to need to transfer all of these to the next node inside. So I'm going to need 1, 2, 3, 4 moves. And so I'm going to need 4 moves. Or rather, I'm going to need 3 moves because I can specify any number. Yeah, I'm going to need 3 moves. But the question is, what's the order I do it in? Because technically, I can't go negative hay bales. Because, like, so for instance, if node 1 had 0 and node 2 had like 3 and I need to get an average of 5 on each node, I can't steal 5 from 3 because that doesn't work. So, okay, so here's what we have now. What we have now is some sort of ordering where basically I know that I'm going to need to go along this edge, and this edge, and I know exactly how much needs to travel, and I know which direction it needs to travel in. So what do? Well, anything which has excess we can push first, and then anything which needs to steal stuff we can pull. But the question is, what order we pull in? And that is a good question. Okay, maybe we're thinking about this wrong. So, suppose now we have the same diagram again, right? I'm going to make it a bit more clear what's going on here. So there we go. So now let's take our line and we're going to go there, take our line and we're going to go there, take our line and we're going to go there. Okay, so nodes 1, 2, 3, 4, right? And we calculated our excesses, -1, -2, +1, +2. Okay. So what I can do here is I can run a BFS, I think. Okay, this is the same solution, actually. I just realized this is the same solution, but I can just run a BFS. So, okay, let's go back. So, what I do know is that, okay, I know which edges need to be moved in this scenario, but I won't always know which ones need to be moved in future scenarios. Okay, what if we approach this from a subtrees manner? So here we go. So what if I consider this in a subtrees manner? So if I have a subtree, so for instance, if I'm considering the subtree of 2, then I know that it's going to have some positives and some negatives. So in this case, if we let's consider the subtree of 1, actually. So we'll start with the subtree of 1. So the subtree of 1 in total has a net gain of 1, which is good, which means there needs to be one. We already know that there needs to be one flow up to here, right? So if I consider this subtree, after all the operations on this subtree are done, like anything going in versus anything pulling out, I know that this has to be 0, right? After everything is done, this subtree has to be 0. So if I calculate the sum of what's already in there, then right now I know that the sum is already +1, which means there needs to be some outwards route of +1. So there needs to be some way to pull out, to push out of +1. Now, since this entire thing needs to push out +1, that means it has one excess, means the entire subtree itself can be solved like within itself, right? This entire thing can be solved. That doesn't work. So like I'm either going to need to pull some amount out or I'm going to need to push some amount in, right? That's what the subtree sum is telling me. So I'm either need to pull or push. If I need to push, that's the problem is if I need to pull stuff out, because if a subtree has a positive gain, then what I can do is I can just solve the subtree, or like if we have some way to solve the subtree, then just solve the subtree and push out, right? Push whatever excess is out. But the problem is if I need to pull stuff in, because then solving the subtree involves pulling stuff in. So let me explain what I mean. So suppose we only ever have to push stuff out of our subtrees. Then what I can just do is I can say solve and create a function solve, like a recursive solve. And what it does is just solve for all adjacents of I, right? So that's going to solve it. For instance, in the subtree, it's going to solve for in the subtree for 2, it's going to solve 3, and then it's going to solve 4. And then what I'm going to do is I'm going to, and since we only have to push, it's going to pull everything from adjacents of I, right? Because adjacents of I are going to push to this node. And then I'm going to push, and then that's it, right? Because now this is going to have some excess. So we already know what the sum is, so now that's it. And then, so when we start with 1, it's going to solve this 2, whatever 2 is going to do, and then it's going to pull whatever 2 gives, and in that case, that's 1. And then when it's doing 2, it's going to solve 3, it's going to solve 4, and then it's going to just pull them up. So that is what we do, but that assumes that we don't have to push anything down, right? So that assumes that 1 is never going to have to push stuff down, and that is clearly wrong when we consider something like this. So if I were to reorganize this tree in this following way, okay, so let me just reorganize this tree like this. So I'm going to start with node 3. It's going to be the same exact tree, okay? Start with node 3, and then we're going to go to node, oops. There we go. And we're going to go to nodes, what is it? 2. So start at node 3, go to 2, and then go to 1, and then go to 4. Okay, right? So if we consider this subtree right here, okay, let me just plug in the values here. So this is going to have a +1, this is going to have a -2, this is going to have a -1, and this is going to have a +2. So if I consider this subtree right here, right, this one, right? Okay, this is horrible boxing, I apologize. But if I consider this subtree, then what I'm seeing here is this subtree has a sum of -1. Which means there needs to be some push into the subtree. So I can never solve the bottom subtree until I push into it, which is a huge problem. So what I want to do is, so I already know that in my entire subtree is going to be 0. Like my entire tree is going to be a 0, right? This entire thing is a 0. So there are 2 cases. Case 1, this is our root node is going to push stuff down. In which case, no hesitation, no worries, just push. Case 2, we're going to need to pull stuff up. In which case, okay, that means that the subtree below it, like every single subtree below it, the subtrees below it, are good. But, oh, there is a problem. There's a problem. Okay, so what if I did this? Okay, so here's what I'm saying. So I know that my entire thing, I'm going to start at some node, and it's going to have, like, some child nodes, right? And then these child nodes are going to have, like, some... Okay, what are you doing? These child nodes are going to have, like, some other child nodes of their own, right? It's going to go down, it's going to go down, it's going to go down, right? Stuff like that. So if I consider this is the root node, right? Root node. And this has something like, say... Obviously, this one's going to have... I don't know, let's say, I don't know. We'll figure that out later. But suppose this one needs 1. This one also needs 1. This one will give 1, and this one will give 1, right? And suppose these are like their subtree values, right? So in this entire subtree, right? This entire subtree, right? This entire subtree right here is going to need 1. This entire subtree right here is going to give 1. This node is going to need 1. And this entire subtree right here is going to give 1 as well. So the thing is, these have to push up, and then this one will push down. So I think we have a solution. We solve everything that has a positive, right? So that pushes stuff. Or that has like a plus, right? So we solve everything that has a plus. So we solve everything that has a plus, and then we pull everything from everything that has a plus, and then we push down to something that has a minus. And we push as much as we need down to something that has a minus. That is our solution. Booyah, we have it. So here's what it looks like. So it's a recursive DFS-ish solve. Okay, so here's solve. So we start at solve from a node, right? Okay, so now what we do is we say for I in edge of node, right? And so suppose we already pre-computed like how much each subtree needs. So if needs of I is greater than 0, or even greater than or equal to, honestly, because if it's equal to 0, we can just solve it. Then solve of I, right? And then how much ever, or this isn't technically needs. This is gives actually. This is gives. This is gives. And then how much ever that subtree is gonna give, we're gonna pull it all out. So we're going to like to our answer, or we're gonna just basically actually just like I don't know how do I put it. Answer.append of we're going to send from node I to node whatever it gives. And this is assuming that it's let me drag over. This is assuming that actually it's greater than 0, but that's a minor thing, so we can overlook that. So let me just drag all of you over there. So answer.append of I node and then how much ever it gives. And this one is assuming that this answer.append is assuming that actually it's greater than 0, but that's kind of not necessary. That is necessary, but that's something that's not necessary to put in the pseudocode. Okay, and so if it gives, we're going to do that. And then for I in edge of node. So once we've done all of this, so all the positive and 0 are handled. If it's less than 0, then we want to answer.append of I or node, and it's going to give this to I, and it's going to give how much ever gives of I needs, right? How much ever it needs, and then we solve of I. And this is actually a function, not a square brackets. Then we solve I. And this one is then we solve I. And that should be the entire solution. That's it. Yeah, this should work. And then we just recursively, this recursive call is called in node 0. Okay, so let's begin coding this up. So we're going to include our usual things, and then int main, and int n, right? Sin n. So there are a couple of things that we're going to need. We're going to need a vector of int, and this vector is, and actually there's going to be long longs because the values go up to 10 to the power of 9. So vector of long, and we are going to need to store our like differences. So I'm going to call this diff, and actually we'll keep it like that. And diff dot resize of n, and for long n I in diff, we're going to input I. And so then total equals accumulate of diff dot begin, diff dot end, and 0, right? So now tot divided by equals n, and so then for long n I in diff, we're going to say I minus equals tot. So this is going to give us, if we take a look here, this will be all of these -1, -2, +1, +2, all of those values. So now what we need to do is input our adjacency list. And so for that, we're going to go here to vector of vector of int. And then this is going to be our adjacency list, right? So adjacency list, so adj.resize of n, and then for int I is equal to 1, I is less than n, I plus plus, right? So this is going to give, wow, this is going to give me n minus 1 things. So int a, b, sin a, b, a minus minus, b minus minus, an edge of A dot pushback of B, an edge of B dot pushback of A, right? Okay, there we go. So now that our adjacency is fulfilled, we're going to need a couple of things. We're going to need a vector of int subtotal, and so this is going to give me the subarray total, so that's going to be like this thing right here, where this is +1, +1, -1, right? And the subtotal of this one is -1. So the way that we'll do that is with a DFS, obviously. But so for now, subtot.resize of n. And so now we're going to need to create a void. I don't want to call it DFS, I'm just going to call it sub. And it's going to take in a node and a parent. And what it's going to do is essentially just, yeah, this will be long actually. So long rem or st is equal to 0, right? For in I is equal to 0, or I, actually for in I an edge of node, if I is equal to parent, continue, right? And so if it's not equal to parent, that means that we want to first, we want to go and so sub of I, and then node is the parent, right? And then st plus equals, or rather, actually, st here is going to equal diff of node, okay? Diff of node. Okay, now st plus equals subtot of I, right? And then subtot of node is equal to st. Okay, so now that that's done, we can dff or sub of node, or sub is 0, 0, right? Okay, and then now we need to run our actual DFS. So we're going to need to keep track of a vector of array of int 3, and this is going to be long. So array of long size 3, and this is going to be our output, so I'm going to say out. And now we need a DFS method. So void DFS int node int parent. This time we're going to have our, so let's take a look here. This is exactly what our algorithm is, by the way. So for int I in edge of node, right, if subtot, which is our gives here, of I is going to be greater than or equal to 0, then solve, or DFS in this case, of I, and here we're going to have parent, right, and solve of I parent, and then we're going to say out.pushback, and we're going to have from node I to node, and we're going to do subtot of I, right, and that's great. And this is only if subtot of I is greater than 0. Okay, and now for int I in edge of node, if subtot of I is less than 0, then we're going to out.pushback. Oh, and these are not the correct type of curly braces, so we're going to just go ahead and fix that. Okay, out.pushback, and in this case, it's going to go from node to node I, and it's going to be negative subtot of I. Wonderful. And then we're going to DFS I parent. Wonderful. And that's it. So now we can DFS on 0, 0. And we can for auto I in, wow, auto I in out, sout I of 0, I of 1, I of 2 slash n, and op, just to make sure it is source barn destination barn, hay bales to move. Great. And before we do that, we should out.size /n. Okay. And that's it. Okay, let's check this out. Hopefully this algorithm works. It should work because we're only moving what we need to move. Barn tree.cpp -o barn tree.cpp, right? And we're not going to do that. We're going to do barn tree. Okay. And then /barn tree. And we're going to pipe it to barn tree.out. Okay. So we're going to copy this input. And it's address error, which is not good. Did I forget to resize something? All right, well, you know what they say. When in doubt, sout it out. Check 2 and check 3. Okay, so let's see. We're passing checks 1 and check 2. We're not passing check 3. Okay, that's DFS 0, 0. Oh, that's why. Okay, easy fix. There we go. Okay, now let's try it. Oh. Okay, looks like we need these still. Still check 1, check 2, so DFS has been changed, but it still doesn't work. So why is that the case? That's the case because I am not even checking. If I is equal to parent, continue. Okay. And we got to do the same thing here. All right, now let's try it. Check 1, check 2, so 3. So we're moving from 2 to 1, 1. All right, let's check this out. All right, let's check this out. It's the right solution, but I need to output +1. So +1 here, and +1 here. Okay, let's try this one out now. Oh, and actually, let's comment these out. Okay. All right. 3, 2, 4, 2, 2, 2, 1, 1. Okay, let's submit, and hopefully it works. Okay, so barntree.cpp, submit solution. And we wait for the X's to roll in. And it's still grading. Or it looks like the checks roll in, which is great. The green dot star 500. Oh, that's taking quite a bit of time. I'm just running 2 DFSs. No, okay. It's taking less than a second. That's good. Bit of knuckle cracking, and we're done. Okay, so that's it. So since it looks like it's running in 877 milliseconds, let's quickly go and take a look at what the actual solution is here. So here's the actual solution. So if every barn has the same number of hay bales in the end, each must have the average. So we'll subtract the average for convenience. So now our objective is to make hi equal to 0. Yep, that's exactly what we did. So consider the 2 subtrees resulting from erasing the... For each edge, consider the two subtrees resulting from erasing the edge. If the sum of either subtree is non-zero, this edge must be used to transport some hay-bales. Thus, our answer is the least number of edges. In fact, this lower bound is achievable using a recursive solution. First, root the tree arbitrarily. Let sum of x be the sum. Okay, yeah, distribute. We distribute the hay bales in x's subtrees so that each node is left with 0 hay bales, except possibly the root, which will have sum of x hay bales. Okay, yeah, so distribute x plus for all children x plus of x such that sum of x plus is greater than or equal to 0. Transport sum x plus. Yes, yes, yes. This is exactly what we did. Okay. And here is their solution. And let us... Wow, that sounds very... What is... Oh, they use a tuple. Oh. I don't know you could do that. Interesting. So let's see how our solution compares to theirs. And this should be CPP, not CP. Okay, so let's check it out. So we're going to go C++17. So just to recap, our solution runs in 877 milliseconds. Actually, this one runs in 891, so we're going to consider that. 891 milliseconds, so around 900 with a 35-ish MB sol. So let's check how theirs does. Theirs seems to be around the same speed as ours. No, theirs is arguably faster. Ooh, this is faster. This is slightly... Is this faster? Yeah, this is faster. Why is theirs faster? It's because... Average divided by equals n. M placeback. They're using M placeback. I'm using pushback. That could be one thing. Okay, but theirs is using less memory and is faster, which is weird. But you know, it's whatever. Okay, yeah. So that means we found the intended solution. So I'm just gonna go ahead and delete this. We found the intended solution, which is, just to recap, I don't know what they were thinking about, like deleting an edge and all that, but essentially, if I'm considering this subtree and this subtree below it has a positive sum, it needs to push something out. If the subtree has a negative sum, it needs to pull something in. It's just that simple, right? So yeah, that's it. Because if this subtree has a negative sum, then that means the rest of the subtree... Okay, I see what they mean by delete, but yeah. But if this subtree has a negative sum, right, then it needs something to come inside, so it needs to have something pulled through this route. And so that's exactly what we're doing. We're saying, okay, for anything which is positive, we're going to solve it, then we're going to answer it, and then for anything which is negative, we're going to answer and then solve. And so that's it. That's exactly what it goes. And that's the solution. So let's just recap the code here. So we have, I do not want to do that. So we have our four arrays implemented here. Diff, which calculates the difference, which is basically just like, is it +1, is it -1, how much does it need to change to go to the average? Adj and subtot. Adj is our adjacency list. Subtot is how much, it's basically diff, but instead of for the node, it's for the subtree. And then out, which is our answer. And so here we have sub, which is basically just filling in the subtot with how much each subtree is. And we have DFS, which is doing our calculating for out. So we're going through the for loop here, And then if I is equal to parent, continue, because we don't want to, that's basically just standard DFS. And if it's greater than or equal to 0, then we're DFSing through because it's positive or it's non-negative. And if it is positive, that means it has to give something. We're putting it to out. And then same thing for negative, where if it's negative, we're basically transferring the hay bales down to the nodes that need it. So that's our answer. And then we're DFSing to that subtree because now it has enough to set it to 0. And so in our main function, we're just filling in our DFS and then filling in our diff and then filling in our diff again, and then like adjusting it so that now it's like adjusted for the average. And then we're inputting our adjacency, and then we're calculating our subtotal, DFSing on 0, 0, which is basically just getting our answer and then outputting our answer. And that's it. Yeah, so this is like a live solve. So I actually didn't know how to do this until we started. So hopefully this shows kind of the process in which I think. Where originally I was thinking like, okay, like getting the adjusting for average is a pretty straightforward thing. Originally I was thinking maybe we should do BFS, and then I kind of took a look at subtrees approach and figured out, okay, no, DFS is exactly what we want here. And then how do we get the subtree approach to work? Well, we're going to want to go to positives first and then negatives later. And yeah, that's it. So if you guys enjoyed, please don't forget to leave a like and subscribe, and let me know down in the comments which problem you'd like me to do next. It looks like USACO problems are a bit more popular with you all, so that's why I'm just doing some more USACO problems. And yeah, I'll catch you all in another video.